Suppose a solution to the equation 3 sin x plus 4 cos x is equal to 0 is required. We could reduce it to a basic one that contains only one trig ratio by dividing throughout by the cosine of x. And this will give us 3 tan x plus 4 is equal to 0. Rearranging that equation to isolate tan x will give us minus 4 over 3. Now we can solve this equation with ease. If you're however unsure of how to find this general solution, please refer to one of my tutorials that deals with the solution of basic trig equations. However, we face some challenges if we are now required to find the solution to the equation 3 sin x plus 4 cos x is equal to, say, 1. Dividing throughout by cos x in this case will give us 3 tan x plus 4 being equal to 1 over cos, which can be written as sec x. And this here is not a basic equation. We can solve this equation by squaring both sides. However, this results in a very lengthy process which is undesirable under examination conditions. So there must be a shorter way which will enable us to get to the solution, and this is the focus of this tutorial. A graphical analysis of the situation here is key to our understanding of the method that we're going to derive today. So if I plot the graph y is equal to 3 sin x plus 4 cos x and the line y is equal to 1, you will agree with me that the points of intersection of these two graphs here will give us the solution of our original equation that is marked here. I have done that. The red graph represents the equation 3 sin x plus 4 cos x, and the blue line represents the line y is equal to 1. Now the points of intersection in the given range give us the solutions to the two equations. I want to draw your attention to the red graph. It does look like a sine wave. You can see that. And I will draw the graph of y is equal to sine x on the same axis, and that is shown by the green graph. I think you'll agree with me that we can transform this green graph into the red one. If I shift the graph to the left, it will look a lot similar to the red one. Certainly the points of intersection with the x-axis, it looks a lot closer at that point. They do coincide. Now the difference between the two graphs is just going to be the depth of these troughs here, which we call the amplitude of the two graphs. Now if I change the amplitude of the green graph, is it possible to make it look like the red one? Let's have a look. You can see it's getting closer and closer to the red one. I'm going to argue that the two graphs are now very close to each other after a transformation. We changed where it cuts the x-axis on the green graph, and we also changed the amplitude of the original green graph to make it look like the graph of y is equal to 3 sin x plus 4 cos x. Now I want to draw attention to the form of the equation of the green graph after the transformation. Have a look here. There is a value 5 sine and x. We are adding 50 degrees to x. This suggests that the equation 3 sin x plus 4 cos x can actually be written in terms of sine x only. Now we can use algebra to determine accurately this value and the value here and that value inside the bracket, and this is the focus of our tutorial. So the new form of the equation suggests that 3 sin x plus 4 cos x can actually be written as r, you saw that 5 there, sine x plus some angle which I'm going to call alpha. Now we want to determine these two values here. Now I can expand the right hand side of this expression using the compound angle formula and make it identical to r sine x cos alpha plus r sine alpha cos x. Now, if the left-hand side is going to be equal to the right-hand side, then the coefficient of the corresponding terms are going to have to be the same. So if I go ahead and equate coefficients of the terms in sine x, on the left-hand side the coefficient is 3, and that should be equal to the coefficient on the right-hand side, which is r cos alpha. I'm going to call this equation 1 because we'll need to refer to it at a later point. Doing the same, taking coefficients of cos x on the left hand side, it is going to be equal to 4. So 4 is equal to the coefficient of cos x on the right hand side, which is r sine alpha. I'll call this equation 2. This angle alpha could be formed by rotating a line of r units on the Cartesian plane as shown here. So let's suppose we start off with a line of r units and we rotate it to some position here, and in the process we create an angle alpha. If I drop a perpendicular here, that will create a 90-degree triangle, and so let me just label my x's. So it follows that from here to there, this distance is going to be equal to x units, and that distance will be equal to y units. I've already said that this length, we're calling it r units. Now, using your basic trigonometry, you will agree with me that sine of alpha is going to be equal to the opposite side, which is y units divided by the hypotenuse, so that y is equal to r sine alpha. Using a similar argument, you will find that x is going to be equal to r cos alpha. Now, by Pythagoras Theorem, we know that x squared plus y squared should be equal to, well, x is equal to r cos alpha, so that has to be squared as well, r cos alpha squared, plus y squared, which is r sine alpha, and that is also squared. If I expand the right hand side and get rid of the brackets, I'm going to have x squared plus y squared being equal to r squared cos squared alpha plus r squared sine squared alpha. Now there's a common factor of r squared on this side, so continuing here, x squared plus y squared should be equal to r squared into brackets cos squared alpha plus sine squared alpha. But this is equal to 1, so this implies that your x squared plus y squared is going to be equal to r squared. In other words, r is going to be equal to the square root, the positive square root of x squared plus y squared. I'm taking the positive square root because we have already said that r is the length of a line, and the length of a line cannot be negative. So what this means for our current example is that since x is equal to r cos alpha, we can argue that x is equal to 3. And since y is equal to r sine alpha, we're going to argue that y is equal to 4. So therefore, r is going to be equal to the positive square root of 3 squared plus 4 squared. And if we simplify this, it will be 9 plus 16, and then we'll get the value of r to be equal to 5. Now, how do we find the value of alpha? Using equation 1, we know that 3 is going to be equal to r, and we've just found r to be equal to 5, so it'll be 5 cos alpha, and then we just solve this for alpha, so cos alpha is going to be equal to 3 divided by 5. Now remember, alpha is a first quadrant angle, so it is just going to be an angle which lies between 0 and 90 degrees. So alpha is equal to 53.13 degrees corrected to 2 decimal points. What this then means is that our original equation 3 sine x plus 4 cos x can be written in terms of sine x only as 5 sine into brackets x plus the angle alpha, which we have just found to be 53.13 degrees. Now, going back to the two graphs, it means that the green graph of y is equal to sine x could actually be transformed into the red graph by using the values that we have just calculated. So if I go ahead and edit this graph here, the graph of y is equal to sine x by putting the value of 5 that we've just calculated, and we also know that the inside of that equation should now read x plus 53.13, and I have to make sure that I close that bracket. Now, if these two equations are equal to each other, then the two graphs must coincide when I press enter. And as you can see now, the two graphs coincide, so the two of them are equal to each other. Now we're looking to generalize the process of finding these values. So if we're given a general equation, say, let me change colors here, say a sine x plus b cos x, and our intention is to write it in the form r sine x plus alpha by using the compound angle formula again. A sine x plus b cos x should be identical to r sine x cos alpha plus r cos x sine alpha. So it follows that r is going to be equal to the square root of a squared plus b squared. And then we can use any one of these equations where we say a is equal to the coefficient of sine x on the right hand side, r cos alpha, or b is equal to r sine alpha. Now these two equations can be used to find the value of alpha. The same equation, 3 sine x plus 4 cos x, can be written in terms of cosine of x minus some alpha. How do we go about this? The procedure is really the same. What we'll need to do is expand right hand side, plus 4 cos x, and make it equal to r cos x cos alpha. It's a minus, so that has to be plus r sine x sine alpha. Now if we go ahead and equate coefficients, it follows that 3 is going to be equal to the coefficient of sine x on the right hand side, which is r sine alpha, but we already know that r is going to be equal to the square root of the coefficients of the two terms, so it's 3 squared plus 4 squared, and this here will give us again 5. Now we know that 5 is equal to r, so 3 is going to be equal to 5 sine alpha, and if we isolate the term in sine alpha, we will get alpha being equal to the inverse of 3 over 5, which is 36.87 degrees, corrected 2 decimal places. So it follows that 3 sine x plus 4 cos x is identical to 5 cos of x minus 36.87 degrees. Well, this is the general process for expressing an equation of this form here into one of the trig ratios. Thank you for watching.